In this module, you will learn about the motion of center of mass in a system of particles. Let us consider a system of n particles, with its total mass constant with respect to time. Now, consider particle I from the system. In the graph, its position is marked by vector Ri, and the center of mass of the given system of particles is denoted as R. Then, R is equal to sigma MIRI by M. MR is equal to sigma MIRI, which is equal to M1 R1 plus M2 R2 plus M3 R3 and so on, plus Mn Rn. On differentiating both sides of the expression with respect to time, we get mdr by dt is equal to m1 into dr1 by dt plus m2 into dr2 by dt plus m3 into dr3 by dt and so on, plus mn into drn by dt. mv is equal to m1 v1 plus m2 v2 plus m3 v3 and so on, plus mn vn, which is equal to sigma mi vi. Let this be equation 1, where v is the velocity of the center of mass and vi represents the velocity of the ith particle. Let us discuss with an example. Consider a body A of mass 0.3 kg is dropped from a certain height. At the same time, another body of mass 0.1 kg is thrown up vertically from the ground with an initial velocity of 10 meters per second. Find the initial velocity of the center of mass of the system of these particles. For the body A, if mass of the body is ma, and for the body B, if mass of the body is mb, then ma is equal to 0.3 kg and mb is equal to 0.1 kg. For the body A, initial velocity Va is equal to 0. And for the body B, initial velocity Vb is equal to 10 meter per second. Mass of the system of two particles m is equal to ma plus mb. That is 0.3 plus 0.1 is equal to 0.4 kg. If the initial velocity of the center of the mass of this two-body system is vcm, then m into vcm is equal to mava plus mbvb, or vcm is equal to mava plus mbvb by m, which is equal to 0.3 into 0 plus 0.1 into 10 whole divided by 0.4 equal to 2.5 meter per second. On differentiating equation 1 with respect to time, m dv by dt is equal to m1 into dv1 by dt plus m2 into dv2 by dt plus m3 into dv3 by dt and so on, plus mn into dvn by dt. ma is equal to m1a1 plus m2a2 plus m3a3 and so on, plus mn/an, which is equal to sigma of mi/ai. Let this be equation 2, where a is the acceleration of the center of mass and ai represents the acceleration of the ith particle. Now, let us find the acceleration of the center of mass of the system of two bodies discussed in the earlier example. We will also describe the motion of the center of mass. Solution. If the downward direction is taken as positive and the acceleration of the center of mass is taken as a, then acceleration of a is equal to acceleration of b, which is equal to g. That means a of a is equal to a of b, which is equal to g, and m into a is equal to ma aa plus mb ab. Therefore, a is equal to 0.3 into g plus 0.1 into g whole divided by 0.4, which is equal to g. That means the center of mass of the system of two bodies will have downward acceleration g. Since the center of mass has initial velocity in the upward direction and acceleration in the downward direction, it initially moves up with decreasing velocity and reaches a maximum height and then start moving down. But mi/ai is equal to Fi, equal to the net force acting on the ith particle. Ma is equal to F1 plus F2 plus F3 and so on, plus Fn, which is equal to sigma Fi. The net force on a particle may be an external force or an internal force. Fi is equal to Fi internal plus Fi external. The internal forces are exerted by one particle on another and forms action-reaction forces. F12 is equal to minus F21. The vector addition of all these internal forces acting on all particles adds to 0. Sigma Fi internal is equal to 0. Hence, Ma is equal to sigma mi/ai is equal to sigma Fi external and is also equal to F external. Let this be equation 3. So, the acceleration of the center of mass A is equal to F external by m. What is the physical meaning of this equation? Ma is equal to sigma mi/ai is equal to sigma Fi external and is also equal to F external. 1. The motion of the center of mass of a system of particles is independent of the internal forces. 2. The center of mass moves as if the whole mass of the system is concentrated at it and the external force is acting on it. 3. These conclusions are true for any system, a rigid body or a group of particles. When a spinner bowls, the ball may have a complicated rotational and translational motion, but the center of mass of the ball will have only translational motion. A gymnast performing an event on a pole will have a complicated motion, but his center of mass moves along a parabolic path. What about the linear momentum of the system of particles? We know that mv is equal to m1 v1 plus m2 v2 plus m3 v3 and so on, plus mn vn, which is equal to sigma mi vi, as pi is equal to mi vi. mv is equal to p1 plus p2 plus p3 and so on, plus pn, which is equal to sigma pi. But for a system of n particles, the linear momentum p of the system of particles is p is equal to p1 plus p2 plus p3 and so on, plus pn, which is equal to sigma pi. Hence, p is equal to mv. Let this be equation 4. The total momentum of the system of particles is equal to the product of the total mass of the system and the velocity of the center of mass. P is identical to the linear momentum of the center of mass of the system of particles. On differentiating equation 4 with respect to time, dp by dt is equal to mdv by dt, which is equal to ma equal to F external. F external is equal to dp by dt. This is Newton's second law of motion applicable to the system of particles. If the external force acting on the system of particles is 0, then F external is equal to 0. dp by dt is equal to 0 and p is constant. This is the law of conservation of momentum applicable to a system of particles, which states that if the total external force acting on a system of particles is 0, then the linear momentum of the system is constant. A rigid body may have both translational and rotational motion. In such cases, it is usually convenient to work with the reference frame that is attached to the center of mass of the system of particles. The motion of a rolling wheel can be considered as translational motion of the center of mass and rotational motion of all other particles about an axis passing through the center of mass. As the moon revolves around the earth will also have the motion as shown to keep their center of mass fixed. When the motion of this system is influenced by the sun's attraction, the center of mass of this system will have pure translational motion. You have now reached the end of this module. In this module, you learnt that MA is equal to sigma MI into AI equal to F external. The motion of the center of mass of a system of particles is independent of the internal forces. The center of mass moves as if the whole mass of the system is concentrated at it and the external force is acting on it. The total momentum of the system of particles is equal to the product of the total mass of the system and the velocity of the center of mass. F external is equal to dp by dt. This is Newton's second law of motion applicable to the system of particles. If the external force acting on the system of particles is 0, then F external is equal to 0, dP by dt is equal to 0, and P is constant. This is the law of conservation of momentum applicable to a system of particles. If the total external force acting on a system of particles is 0, then the linear momentum of the system is constant. Sometimes, it is convenient to work with the reference frame that is attached to the center of mass of the system of particles.